Imagine you're in a race. You're the fastest thing in existence. Nothing, and I mean absolutely nothing, can overtake you. You are light itself, traveling at 299,792,458 meters per second. You are the ultimate speed champion of the universe, the cosmic speed limit that Einstein himself declared unbreakable. But here's something that's going to shatter everything you thought you knew about speed, about physics, and about the very fabric of reality itself. Right now, at this very moment, there are galaxies moving away from us faster than light, not approaching light speed, not at light speed, faster than light, and they're not breaking any laws of physics. In fact, this is exactly what physics predicts should happen. How is this possible? If Einstein proved that nothing can move faster than light, how are entire galaxies doing exactly that? The answer is so mind-bending, so counterintuitive, that when you truly understand it, you'll never look at the night sky the same way again. This isn't just about galaxies or space. This is about discovering that the universe operates on rules so strange, so beautiful, that they make science fiction look boring by comparison. Here's what's really happening. Space itself is expanding. Not the things in space moving through space, but space itself growing, stretching, creating more space between things. And here's the kicker. This expansion doesn't have a speed limit. The cosmic speed limit only applies to things moving through space, not to space itself. It's like the universe found a loophole in its own fundamental laws. But wait, before your brain completely melts, let me hit you with something even more shocking. Because of this expansion, there are galaxies we can see right now that we will never, ever be able to reach, even if we could somehow travel at the speed of light. We are cosmically quarantined from most of the universe, trapped in an ever-shrinking bubble of accessibility. The universe isn't just expanding, it's leaving us behind. Over the next 3 hours and 20 minutes, we're going to go on a journey. We're going to start with the basics of light speed, build up to understanding spacetime itself, and then dive deep into the expansion of the universe in ways that will fundamentally change how you understand reality. By the end of this, you'll understand why some scientists believe we're living in the most special time in cosmic history. A brief window where we can still see evidence of the Big Bang before it expands beyond our reach forever. Before we dive in, smash that like button and subscribe, because this is the kind of deep dive content you won't find anywhere else. And I'm genuinely curious. Drop a comment telling me what country you're watching from and what time it is there right now. I want to see how far across the globe this mind-bending journey reaches. Let's start with a question that seems simple, but will take us down a rabbit hole deeper than you can possibly imagine. Why is light speed the cosmic speed limit in the first place? To understand why galaxies can outrun light, we first need to understand why nothing is supposed to outrun light in the first place. And trust me, the reason is far weirder than you think. Most people learn that the speed of light is 299,792,458 meters per second, and just accept it as a random fact of nature. But it's not random at all. The speed of light is actually the speed of causality itself. It's the speed at which cause and effect propagate through the universe. It's the speed of reality updating. Think of it like this. Imagine the universe is a massive multiplayer video game, and the speed of light is the game's maximum frame rate for processing information. Everything that happens, every interaction, every force, every bit of information can only propagate through the universe at this maximum speed. Light just happens to travel at this speed because photons have no mass. They're pure energy moving at the maximum speed the universe allows. Here's where it gets interesting. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything. Einstein wasn't trying to figure out why nothing could go faster than light. He was trying to solve a much simpler problem. Why do the laws of physics look the same no matter how fast you're moving? Einstein realized something profound. If the laws of physics are truly the same for everyone, regardless of their motion, then the speed of light must be the same for everyone too. This sounds innocent enough, but the implications are absolutely reality-shattering. Here's what I mean. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour. To someone standing still watching the train pass, that ball is moving at 120 kilometers per hour. Speeds add up. This is common sense. This is how the universe should work. But light doesn't play by these rules. If you're on a spaceship moving at 99% the speed of light, and you turn on a flashlight pointing forward, the light doesn't travel at the speed of light plus 99% the speed of light. To you, the light moves away at exactly the speed of light. But here's the part that breaks your brain. To someone standing still watching you pass, that light is also moving at exactly the speed of light. Not faster, not slower, exactly the same speed. How is this possible? How can the same beam of light be moving at light speed relative to two different observers who are moving at nearly light speed relative to each other? The answer is that time and space themselves must be flexible. They must stretch and compress to make the speed of light constant for everyone. This is what Einstein's special relativity tells us. When you move faster, time slows down for you. Distances contract. Your present becomes someone else's past or future. Reality itself becomes observer-dependent. The universe literally reshapes itself to keep light speed constant. But here's what most people miss. Einstein's speed limit only applies to things moving through space. Objects with mass, particles, information. Anything moving from point A to point B through space cannot exceed light speed. The law is absolute and unbreakable for anything moving through space. Through space. Remember those two words. They're about to become the most important loophole in physics. In 1915, Einstein published his general theory of relativity, which was even more mind-blowing than special relativity. General relativity revealed that space and time aren't just flexible. They're not even separate things. They're unified into something called spacetime, a four-dimensional fabric that can bend, twist, and warp. Massive objects like stars and planets create dips and curves in spacetime, kind of like how a bowling ball creates a dip when you place it on a stretched rubber sheet. What we call gravity isn't actually a force pulling things together. It's objects following the curves in spacetime created by mass and energy. But here's what's crucial. In general relativity, spacetime itself is a dynamic thing. It can bend, it can wave, it can vibrate, and yes, it can expand. Spacetime isn't just the stage where the universe plays out. It's an active participant, capable of motion and change. And here's the kicker that Einstein himself initially refused to believe. The equations of general relativity predict that spacetime itself should be either expanding or contracting. A static universe, one that just sits there unchanging, is actually impossible according to Einstein's own equations. Einstein was so bothered by this that he added a fudge factor to his equations called the cosmological constant, essentially a repulsive force that would hold the universe still. He later called this the biggest blunder of his career. Why? Because in 1929, an astronomer named Edwin Hubble made a discovery that changed everything. Hubble was studying distant galaxies using the 100-inch telescope at Mount Wilson Observatory in California. He was measuring their spectra, the specific wavelengths of light they emitted, and he noticed something strange. The light from distant galaxies was shifted toward the red end of the spectrum. The farther away the galaxy, the more redshifted its light was. This redshift meant the galaxies were moving away from us, but not just moving away randomly. The farther away a galaxy was, the faster it was receding. Hubble had discovered that the universe itself is expanding. Think about this carefully. Hubble wasn't seeing galaxies flying through space away from us. He was seeing space itself expanding, carrying the galaxies along with it like raisins in rising bread dough. As the dough expands, the raisins move apart, not because they're moving through the dough, but because the dough itself is growing. This is the crucial distinction that most people miss. When we say the universe is expanding, we don't mean that galaxies are flying through space away from each other. We mean that space itself is getting bigger. New space is being created between galaxies. The fabric of space-time itself is stretching. And here's where everything we've learned comes together into something truly mind-blowing. Einstein's speed limit says nothing can move through space faster than light. But it says absolutely nothing about how fast space itself can expand. The speed limit applies to motion through space, not to the expansion of space itself. It's like the ultimate cosmic loophole. The universe has a maximum speed limit for everything traveling through it, but the universe itself isn't bound by that limit. The container can grow faster than the maximum speed anything inside it can travel. Let me give you an analogy. Think of it like you're an ant on a rubber band. You can run along the rubber band at your maximum ant speed. That's your speed limit. You cannot run faster than that maximum speed relative to the rubber band beneath your feet. But what if someone starts stretching the rubber band itself? The rubber band can stretch faster than you can run. From the perspective of someone watching, you might be carried along faster than your maximum running speed, not because you're running faster, but because the rubber band itself is stretching. That's what's happening in the universe. Galaxies aren't moving through space faster than light, but space itself is expanding, and that expansion can carry galaxies apart faster than light could travel between them. Now here's where it gets even crazier. In 1998, two teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, made a discovery that won them the Nobel Prize in Physics. They were studying distant supernovae, using them as cosmic measuring sticks to map the expansion of the universe. They expected to find that the expansion was slowing down due to gravity. Instead, they found the exact opposite. The expansion of the universe is accelerating. Not just expanding, but expanding faster and faster over time. Something is pushing the universe apart with ever-increasing force. We call this mysterious force dark energy, and it makes up about 68% of all the energy in the universe. We have no idea what it is. It's one of the biggest mysteries in all of science. But its effects are clear. The universe isn't just expanding, it's expanding at an accelerating rate. This means that distant galaxies aren't just receding from us faster than light. They're accelerating away from us. The universe is running away from itself, and it's speeding up as it goes. But before we dive deeper into the implications of this accelerating expansion, I need to make sure you understand something fundamental about how we measure the expansion of the universe. Because the way astronomers measure cosmic expansion reveals something profound about the nature of spacetime itself. Let's talk about how we know space is expanding in the first place. Because understanding the evidence will make the implications so much more profound. When Edwin Hubble looked at distant galaxies in 1929, he wasn't just noticing that they looked red. He was analyzing their spectra in incredible detail. Every element emits light at specific wavelengths. Hydrogen always emits light at certain wavelengths. So does helium, carbon, oxygen. Every element has its own unique spectral fingerprint. When Hubble looked at the light from distant galaxies, he saw these same spectral lines, but they were shifted. The wavelengths were stretched, moved toward the red end of the spectrum. It's like taking a pattern and stretching it. The pattern is still recognizable, but everything is shifted. This is called cosmological redshift, and it's different from the Doppler shift you experience when an ambulance passes by. The Doppler shift happens when something moves through space toward or away from you. But cosmological redshift happens because space itself is expanding while the light travels through it. Think of it like this. Imagine you draw a wave on a rubber band. then stretch the rubber band. The wave pattern gets stretched too. The wavelength of the wave increases because the medium it's drawn on expanded. That's what's happening to light traveling through expanding space. The light waves get stretched as space expands, shifting them toward the red end of the spectrum. Hubble made another crucial observation. He noticed that the redshift of galaxies correlated with their distance. The farther away a galaxy was, the more redshifted its light was. This relationship is now called Hubble's law, and it's expressed with a simple equation: velocity equals Hubble's constant times distance. The Hubble constant tells us the rate of expansion of the universe. Today, we measure it at about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So what this means is that for every 3.26 million light years of distance, space is expanding at an additional 70 kilometers per second. Let me break this down because it's crucial to understanding how galaxies can exceed light speed. If a galaxy is 3.26 million light years away, space is expanding between us and that galaxy at 70 kilometers per second. If a galaxy is twice as far, at 6.52 million light years, space is expanding at 140 kilometers per second. At 10 times the distance, the expansion rate is 700 kilometers per second. You see where this is going? The speed of light is 299,792 kilometers per second. Divide that by 70, and you get about 4,283 megaparsecs, or about 14 billion light years. Beyond that distance, space is expanding faster than the speed of light. Right now, at this very moment, there are galaxies more than 14 billion light years away, receding from us faster than light. They're not breaking any laws of physics. They're not moving through space faster than light. Space itself is expanding between us and them at faster than light speeds. But here's something that will really bake your noodle. We can actually see some of these galaxies. How is that possible? If they're receding faster than light, how can their light ever reach us? The answer reveals something profound about the expansion of the universe. The expansion rate hasn't always been the same. In the early universe, the expansion was different. Some of these galaxies we see today are now receding faster than light, but when they emitted the light we're seeing, they were closer, and the expansion between us was slower. The light they emitted long ago eventually reached us, but any light they emit now will never reach us. We're seeing their past, but their present is cosmically inaccessible. This leads to one of the most mind-bending concepts in cosmology: the observable universe versus the actual universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. It has a radius of about 46.5 billion light years. Wait, you might be thinking, if the universe is only about 13.8 billion years old, how can we see things 46.5 billion light years away? Shouldn't the observable universe only be 13.8 billion light years in radius? This is where the expansion of space creates something truly strange. When we look at a galaxy 13 billion light years away, we're seeing it as it was 13 billion years ago, because that's how long its light took to reach us. But in those 13 billion years, space has been expanding. That galaxy is now much farther away than 13 billion light years. It's now about 30 billion light years away. We're seeing where it was, not where it is. The observable universe is the sphere containing all the objects whose light has had time to reach us. But the actual universe, the whole universe, is much bigger. It might be infinite. We don't know. We can only see the part of it that's close enough for light to have reached us in the 13.8 billion years since the Big Bang. Now, here's where things get really existential. Because of the accelerating expansion discovered by Perlmutter, Schmidt, and Rees, the observable universe is actually going to shrink in the future. Not in terms of size, but in terms of content. Right now, we can see about 2 trillion galaxies in the observable universe. But as space continues to accelerate, galaxies beyond a certain distance will accelerate past light speed. Once they do, their light will never be able to fight against the expansion of space to reach us. These galaxies will fade from view, redshifting into invisibility, disappearing beyond a cosmic horizon. In the far future, trillions of years from now, an observer in our galaxy will look out and see almost nothing. The accelerating expansion will have carried away all the distant galaxies. The sky will be dark, except for the stars in our local gravitational neighborhood. The galaxies bound together tightly enough by gravity that the expansion of space doesn't separate them. Future astronomers will look up and see a quiet, static universe containing only their local galaxy cluster. They'll have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence that the universe is anything other than small and eternal. They'll be cosmically isolated, cut off from the truth of their own origins. We live in a special time, a time when we can still see the afterglow of the Big Bang, still see distant galaxies, still piece together the history and fate of the universe. We're living in a brief cosmic window of observability, but I'm getting ahead of myself. To really understand how profound this is, we need to go deeper into what the expansion of space actually means. Because there's a question I've been dancing around that you're probably screaming at your screen right now. If space is expanding everywhere, why aren't we expanding? Why isn't your body expanding? Why isn't Earth expanding? Why isn't the solar system expanding? This is one of the most common misconceptions about cosmic expansion. And the answer reveals something fundamental about the nature of space and the forces that govern it. Space is expanding everywhere. Right now, right here, space is trying to expand between atoms in your body, between cells, between you and your computer screen, between Earth and the sun. The expansion of space is truly universal. It's happening at all scales, in all places, at all times. So why don't we notice it? Why doesn't it tear everything apart? The answer is that at small scales, the expansion is ridiculously weak compared to the forces that hold things together. The expansion rate is about 70 kilometers per second per megaparsec. That's 70 kilometers per second across a distance of 3.26 million light years. Scale that down to everyday distances and the expansion becomes infinitesimally small. Let's do some math. A megaparsec is about 3.09 times yp kilometers. So the expansion rate is 70 kilometers per second divided by 3.09 times yp kilometers, which gives us about 2.27 times 10 to 18 per second. That's the fractional rate at which space is expanding. Now let's apply this to the distance between you and your screen. Say you're sitting 1 meter away. That's 0.001 kilometers. Multiply by the expansion rate, and you get about 2.27 times 10 to 21 kilometers per second. That's 2.27 times 10 to 18 millimeters per second. That's about 0.0000007 millimeters per year. The expansion of space is trying to separate you from your screen by about 70 billionths of a millimeter per year. But the electromagnetic forces holding the atoms in your body together and the gravitational force holding you to Earth are trillions and trillions of times stronger than this expansion. The expansion is utterly negligible at this scale. Think of it like this. Imagine you're holding a ball connected to a rubber band anchored to a wall. If someone very slowly stretches the room you're in, making it slightly bigger, you wouldn't notice because the tension in your arm and the rubber band easily overcomes the tiny expansion of space. You'd remain holding the ball at the same distance from the wall, despite the room growing slightly. That's what's happening everywhere in the universe, at small scales. Electromagnetic forces, which hold atoms and molecules together, are vastly stronger than the expansion. Gravity, which holds planets around stars and galaxies, is vastly stronger than the expansion at those scales. Only at truly vast scales, across millions and billions of light years, does the accumulated expansion of space become significant compared to the forces holding things together. Only at those scales does the expansion of space dominate over the other forces. This is why galaxies aren't expanding. The gravity holding them together is too strong. This is why galaxy clusters, groups of galaxies bound by gravity, aren't expanding. But between galaxy clusters, where gravity is weak and distances are vast, the expansion of space takes over. The universe is expanding, but only in the regions where nothing is strong enough to resist that expansion. It's like a tug of war between the expansion of space and the fundamental forces of nature. At small scales, the forces win. At cosmic scales, expansion wins. Now here's something that's going to twist your brain. Because of this interplay between expansion and forces, the expansion of space creates something called a gravitational horizon. And this horizon is the key to understanding why some galaxies are forever beyond our reach. Remember, space is expanding. The farther away something is, the faster space is expanding between us and it. At some distance, space is expanding at exactly the speed of light. This distance is called the Hubble sphere, and it's at about 14 billion light years from us. Now, if you're a photon trying to reach us from beyond the Hubble sphere, you have a problem. You're traveling through space at light speed, but space itself is expanding between you and your destination faster than light speed. You're like a runner on a treadmill that's going faster than you can run. You're moving forward at maximum speed, but you're actually losing ground. This creates a cosmic horizon. Light emitted from beyond a certain distance can never reach us. Not because it's not trying, not because it's breaking down, but because the space between us and the source is growing faster than the light can traverse it. But here's the really weird part. Because the expansion is accelerating, this horizon is getting closer to us over time. More and more of the universe is passing beyond this horizon, disappearing from view forever. The universe isn't just expanding, it's outrunning itself, leaving parts of itself permanently disconnected. Let me give you an analogy. Think of it like you're standing on a road that's magically growing between you and a friend walking toward you. Your friend is walking at their maximum speed, trying to reach you. If the road is growing slowly, your friend will eventually reach you despite the growth. But if the road is growing fast enough, your friend will walk and walk and walk, and despite moving toward you at maximum speed, they'll actually get farther away from you because the road is growing faster than they can walk. That's what's happening with light from distant galaxies. The light is traveling toward us at maximum cosmic speed, the speed of causality itself, but space is expanding between us and the source faster than that. The light is losing ground despite moving at the maximum possible speed. Now let me blow your mind even further. There's another horizon in the universe, and this one is even weirder. It's called the particle horizon, and it represents the most distant objects that we could theoretically see, given that light travels at a finite speed and the universe has a finite age. When the universe began 13.8 billion years ago in the Big Bang, everything was close together. As the universe expanded, light from distant regions started traveling toward us. But light takes time to travel, so we can only see regions of the universe whose light has had time to reach us in those 13.8 billion years. Because of the expansion of space, the particle horizon is actually about 46.5 billion light years away, even though the universe is only 13.8 billion years old. This is that weird effect I mentioned earlier, where distances grow as light travels through expanding space. But here's what's truly bizarre. Beyond the particle horizon, there is more universe. There are galaxies, stars, perhaps even other observers looking up at their sky. But we can never see them, and they can never see us. Not because we're too far apart, not because their light isn't bright enough, but because the universe hasn't existed long enough for light to travel between us, even accounting for the expansion of space. These regions of the universe are not just far away, they're cosmically elsewhere. They exist in the same spacetime as us, but they're disconnected from us by the fundamental structure of causality itself. No information, no light, no signal of any kind has or ever will travel between us and them. And because of the accelerating expansion, this region of cosmic elsewhere is growing. More and more of the universe is slipping beyond the horizon, passing from the category of very far away to fundamentally inaccessible. In 1 trillion years, an observer in our galaxy will look up and see almost nothing. The expansion will have carried away all the distant galaxies beyond the horizon. The cosmic microwave background, the afterglow of the Big Bang that we can see today filling the sky with faint microwave radiation, will have redshifted into nothingness, stretched to such long wavelengths that it becomes undetectable. Future observers will live in a dark, quiet universe with no evidence of the cosmic drama that created them. They'll be living in the aftermath of an event they can no longer see. We are incredibly lucky. We exist at a time when the universe is still young enough. The expansion hasn't yet outrun itself completely, and we can still see the echoes of our cosmic origins. We can still piece together the story of where we came from and where we're going. But to really appreciate how remarkable our situation is, we need to go even deeper. We need to understand not just that space is expanding, but what that expansion actually means for the nature of space itself. Let's talk about what space actually is. Because if space can expand, if it can curve and warp and stretch, then space must be something rather than nothing. And understanding what that something is will transform how you think about reality. For most of human history, we thought of space as just emptiness, the void between things, the nothing in which something exists. It was the stage, the container, the background against which the universe played out. Isaac Newton, the father of classical physics, thought of space and time as absolute. Space was an infinite, unchanging three-dimensional grid. Time was a universal clock, ticking at the same rate for everyone everywhere. Things moved through space, events happened in time, but space and time themselves were immutable backdrops. Then Einstein came along and shattered this conception completely. Einstein's general relativity revealed that space and time are not separate things. They're unified into a four-dimensional entity called spacetime. And spacetime is not passive. It's dynamic. It bends, curves, and warps in response to mass and energy. Massive objects like stars and black holes create deep wells in spacetime. What we perceive as gravity is actually objects following the curved geometry of spacetime. Earth doesn't orbit the sun because the sun pulls on it. Earth orbits the sun because the sun curves spacetime around it, and Earth is following the straightest possible path through that curved geometry. Think of it like this. Imagine a bowling ball placed on a trampoline. The trampoline surface dips down around the ball. If you roll a marble across the trampoline, it curves toward the bowling ball, not because the ball is pulling it, but because the marble is following the curved surface of the trampoline. That's what mass does to spacetime. It curves it. And objects move through spacetime following those curves. Gravity isn't a force pulling things together. It's the geometry of spacetime itself. But here's where it gets truly weird. If spacetime is a dynamic thing that can be curved by mass and energy, then spacetime itself must be made of something. It must have properties. It must be a real physical entity, not just an abstract mathematical construct. So, what is spacetime made of? This is one of the deepest questions in physics, and we don't have a complete answer. But we have clues. Spacetime appears to have a structure at the smallest scales. Most physicists believe that at distances around the Planck length, about 1.6 times 10 to 35 meters, spacetime might not be smooth and continuous anymore. It might be quantized, made of discrete units, like how matter is made of atoms. This is where quantum mechanics meets general relativity and things get truly strange. Quantum mechanics tells us that at very small scales, everything becomes probabilistic and uncertain. Particles don't have definite positions. They exist in superpositions of multiple states simultaneously. The quantum world is fuzzy, indeterminate, nothing like our everyday experience. General relativity, on the other hand, describes space-time as smooth and continuous, curving gracefully in response to mass and energy. These two theories, quantum mechanics and general relativity, are the most successful theories in all of physics. They've been tested to incredible precision and passed every test. But they're fundamentally incompatible with each other. When you try to apply quantum mechanics to gravity, to understand spacetime at quantum scales, the math breaks down. You get infinities, nonsensical predictions, equations that lose all meaning. This is the greatest crisis in theoretical physics. We have two beautiful theories that describe different aspects of reality perfectly, but we can't combine them into a single coherent picture. This is the goal of quantum gravity: to understand what spacetime is at its most fundamental level, to unite general relativity and quantum mechanics into a theory of everything. Several approaches have been tried. String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings. In string theory, spacetime might have extra dimensions beyond the three of space and one of time that we experience. These extra dimensions might be curled up so small that we can't detect them, but they're there, influencing how strings vibrate and giving rise to all the particles and forces we see. Loop quantum gravity takes a different approach. It suggests that spacetime itself is made of tiny loops, discrete units of space woven together like a fabric. At large scales, this fabric looks smooth and continuous, but zoom in close enough and you'd see the individual loops, the atoms of spacetime itself. We don't know which, if any, of these approaches is correct. We don't have the technology to probe spacetime at Planck scales, where quantum effects should become apparent. But what we do know is that spacetime is not just an empty void. It's a real, physical thing with properties and structure. And if spacetime is a physical thing, then it can do physical things. It can vibrate. In 2015, scientists at LIGO detected gravitational waves for the first time. Ripples in spacetime caused by colliding black holes over 1 billion light-years away. These weren't ripples in something moving through spacetime. These were ripples in spacetime itself. Waves of geometry propagating through the universe at light speed. Spacetime can bend. Spacetime can wave. And yes, spacetime can expand. The expansion of the universe isn't the universe growing into anything. It's not like there's empty space outside the universe that it's expanding into. The universe isn't expanding into anything. Space itself is growing. More space is coming into existence. The universe is creating more of itself from within. Think about that. The universe is getting bigger, not by stretching into something else, but by creating more space inside itself. It's like if you had a balloon, but instead of inflating it by blowing air into it, the rubber of the balloon itself was multiplying, creating more balloon from nothing. This is where the expansion of space differs fundamentally from motion through space. When something moves through space, it's relocating from one part of spacetime to another. It's changing position in the existing grid. But when space expands, it's creating new grid, new space that didn't exist before. And here's the truly mind-bending part. The expansion of space doesn't require any energy. Creating space doesn't take fuel or power. It just happens. The equations of general relativity allow for solutions where space-time expands. And that expansion is a natural evolution of space-time geometry given certain initial conditions. In fact, in the early universe, a fraction of a second after the Big Bang, space expanded extraordinarily rapidly in a period called cosmic inflation. In less than 10 to 32 seconds, space expanded by a factor of at least 1026. The universe grew from smaller than an atom to larger than a grapefruit in a time span so short we can barely comprehend it. This inflation was driven by a quantum field that permeated space. As this field settled into its lowest energy state, it released energy that drove the expansion. But here's the key. Even though energy was being released, the expansion didn't require energy input. The expansion was a property of spacetime itself. This brings us to one of the most profound mysteries in cosmology. If the expansion of space doesn't require energy, if it's just a natural evolution of space-time geometry, then where did all the space come from? How can the universe create something from nothing? The answer might be that the universe isn't creating something from nothing. It might be that the total energy of the universe is actually zero. The positive energy locked up in matter and radiation might be exactly balanced by the negative gravitational energy of all those masses attracting each other. The universe might be the ultimate free lunch, a zero-sum cosmic bookkeeping where everything balances out. This idea was proposed by physicist Alan Guth when he developed the theory of cosmic inflation in 1980. If the total energy is zero, then the universe doesn't need to violate conservation of energy to expand and create more space. It's just redistributing zero into different forms. But before your brain completely melts, let me bring this back to our original question. We've established that space is expanding, that this expansion doesn't violate Einstein's speed limit because space itself isn't bound by that limit. And that space is a real physical thing that can expand without requiring energy input. Now we need to tackle the question that makes all of this even more mind-bending. What happens at the edge where space is expanding faster than light? Imagine you're a photon emitted from a galaxy far, far away. You're traveling through space at light speed, the cosmic speed limit, the fastest anything can move through spacetime. You're heading toward Earth, carrying information about the galaxy you left behind. But space between you and Earth is expanding. Every second, more space is created between you and your destination. You're running forward at maximum speed, but the finish line is moving away from you. Now here's the question. Do you ever reach Earth? Can light from beyond the Hubble sphere ever make it to us? The answer is surprising and reveals something profound about the expansion of the universe. It depends on whether the expansion is accelerating or not. In a universe where expansion is constant, photons from beyond the Hubble sphere can eventually reach us. Here's why. As the photon travels, it enters regions where space is expanding more slowly relative to its current position. Remember, expansion rate depends on distance. The farther you are, the faster space expands. But as the photon gets closer to us, it's entering regions where the local expansion relative to its position is slower. Think of it like running on a treadmill that's slowing down as you run. At first, you're losing ground because the treadmill is moving backward faster than you can run forward. But as the treadmill gradually slows down, eventually you start making progress. Your running speed stays the same, but the backward motion of the treadmill decreases until finally you're moving forward faster than the treadmill is moving backward. That's what happens to photons in a universe with constant expansion. They start out in regions where space is expanding faster than light speed, but as they travel closer to us, they enter regions where the expansion is slower. Eventually, they cross into regions where the expansion is slower than light speed, and from that point on, they make steady progress toward us. This is why we can see galaxies that are currently receding from us faster than light. The light we're seeing was emitted billions of years ago when those galaxies were closer. That light has been fighting against expansion all this time, and it finally made it to us. But here's the thing. Those galaxies are now much farther away, and any light they emit today will have a much harder time reaching us. In fact, in an accelerating universe, which is what we live in, there's a cosmic horizon beyond which light emitted today will never reach us. Not in 1 billion years. Not in 1 trillion years. Never. This horizon is called the cosmic event horizon, and it's currently at about 16 billion light years from us. Any light emitted today from beyond that distance will never make it to us because the accelerating expansion keeps pushing the finish line away faster than the light can approach it. Think about this carefully. Right now, at this very moment, there are galaxies beyond this horizon. They exist. They're real. They're out there somewhere in space-time. But they're causally disconnected from us. Nothing they do, no light they emit, no signal they send will ever reach us. And nothing we do will ever reach them. These galaxies are not in our future. They're not in our past. They're in a region of space-time that has no causal connection to us whatsoever. They might as well be in a different universe entirely. And because of the accelerating expansion, this horizon is getting closer to us. Well, not exactly closer in distance, but more galaxies are crossing it. Galaxies that we can see now will eventually cross this horizon and disappear from view, fading into invisibility as their light becomes so red-shifted that we can no longer detect it. Let me paint a picture of what this means for the far future. In about 100 billion years, the accelerating expansion will have carried away all the galaxies beyond our local gravitational neighborhood. An astronomer in our galaxy, assuming our galaxy still exists and has stars and planets capable of hosting life, will look up and see only the stars and galaxies gravitationally bound to our local group. They'll see no cosmic microwave background, no evidence of the Big Bang, no distant galaxies, no indication that the universe is expanding. They'll think they live in a small, eternal, static universe consisting of just their local galaxy cluster, surrounded by infinite empty space. They'll be cosmically isolated, cut off from the truth. All the evidence that would tell them about the Big Bang, about cosmic expansion, about the 13.8 billion year history of the universe, will have been erased by the expansion itself. We are incredibly, unbelievably lucky. We exist at a time when the universe is still young enough that we can see the evidence of our origins. We can still see the cosmic microwave background, the afterglow of the Big Bang. We can still see distant galaxies and piece together the expansion history. We can still do cosmology. This was pointed out by physicist Lawrence Krauss in his book, A Universe from Nothing. We live in a brief cosmic window of observability. Before this window, the universe was too hot and dense for stars and planets to form. After this window, the expansion will have erased the evidence. We exist in a cosmically special time. But here's something even weirder. Because of the expansion of space and the cosmic event horizon, we can actually see farther than we can ever travel, even if we could move at light speed. Right now, we can see galaxies that are about 46 billion light-years away in co-moving coordinates, accounting for expansion. But the cosmic event horizon is only about 16 billion light-years away. This means we can see galaxies that we could never reach even if we left today traveling at light speed. If we left Earth today on a spacecraft traveling at light speed, we could eventually reach any galaxy currently within the cosmic event horizon. It would take a long time, and the galaxy would be much farther away when we arrived than it is now, but we could reach it. But galaxies beyond that horizon are forever beyond our reach, even though we can see them. We're looking at places we can never go. We're seeing parts of the universe that are, in a very real sense, outside our universe, outside the region of space-time we can ever influence or be influenced by. Think of it like this. Imagine you're on an island, and you can see other islands in the distance. Some of those islands are within swimming distance. If you start swimming now, accounting for the currents and waves, you could eventually reach them. But some islands are so far away that even if you swim at maximum speed, the currents will carry them away faster than you can approach. You can see them, but you can never reach them. They're in view, but not in reach. That's our cosmic situation. We can observe, but not access large parts of the universe. Now let me hit you with something that's going to make all of this even more mind-bending. Everything I've told you so far assumes that space is fundamentally smooth and continuous, that general relativity is the correct description of space-time at all scales. But there are hints, tantalizing suggestions from quantum mechanics and high-energy physics, that this might not be true. At the smallest scales, at the Planck length of about 10 to 35 meters, space-time might not be smooth. It might be grainy, quantized, made of discrete units. And if that's true, then the expansion of space might be something even stranger than we thought. Imagine if space-time is like a digital image. At normal viewing distances, it looks smooth and continuous. But zoom in far enough, and you see the individual pixels. Now imagine this image is expanding, not by stretching the pixels, but by adding new pixels between the existing ones. The resolution is increasing. The image is becoming more detailed, more expansive, but the fundamental units remain the same size. That might be what's happening with the expansion of space. New Planck scale units of spacetime might be popping into existence, adding to the fabric of reality. Space isn't stretching like a rubber band. It's multiplying like cells dividing. If this is true, then the expansion of space is literally the creation of new spacetime from nothing, or more accurately, from quantum fluctuations in the vacuum. The quantum vacuum isn't really empty. It's seething with virtual particles popping in and out of existence, borrowing energy from the vacuum and paying it back so quickly that you can't detect them. This quantum foam, as it's called, might be what's driving the expansion. Tiny fluctuations in quantum fields might be creating new space at the Planck scale, and all those tiny additions add up to the cosmic expansion we observe. This is speculation. We don't have a confirmed theory of quantum gravity that tells us exactly what's happening, but it gives you a sense of just how strange and profound the expansion of space might be at its most fundamental level. Before we go further, I want you to do something. Hit that subscribe button if you haven't already, because we're about to go even deeper. We're going to explore what the expansion of space means for the ultimate fate of the universe. And trust me, it's both terrifying and beautiful. And drop a comment right now. Does the fact that most of the universe is forever beyond our reach make you feel small and insignificant? Or does it make you feel special to live in a time when we can still see cosmic history? I'm genuinely curious about your perspective. Let's talk about the end. Because if you really want to understand the expansion of space, you need to understand where it's taking us. And the answer is both beautiful and terrifying in ways that will change how you think about existence itself. For most of human history, people thought the universe was eternal and unchanging. The stars were fixed in their celestial spheres. The cosmos was static and permanent. Even after we discovered that Earth orbits the sun, that stars are distant suns, that galaxies are massive collections of billions of stars, we still thought the universe itself was eternal. Then in the 1920s and 1930s, everything changed. Hubble discovered expansion. Georges Lemaître, a Belgian priest and physicist, worked backward from the expansion and realized that if space is getting bigger, it must have been smaller in the past. Rewind far enough, and the entire universe must have been compressed into an infinitely small point. Lemaître called this the primeval atom. Others mockingly called it the Big Bang, a name that stuck even though it's misleading. The Big Bang wasn't an explosion in space. It was an explosion of space. It was the moment when space itself began expanding from an infinitesimally small, infinitely hot, infinitely dense state. The universe had a beginning. This was a revolutionary, almost heretical idea. It implied that the cosmos wasn't eternal, that time itself had a starting point. It raised uncomfortable questions about what came before, about what caused the Big Bang, about why there's something rather than nothing. But the evidence became overwhelming. The cosmic microwave background, discovered by accident in 1964 by Arno Penzias and Robert Wilson, was the smoking gun. This faint microwave radiation filling the entire sky is the cooled afterglow of the Big Bang itself, light that has been traveling through space for 13.8 billion years. stretched by expansion into the microwave part of the spectrum. So the universe had a beginning. It's been expanding for 13.8 billion years. The natural question is, how will it end? For decades, cosmologists thought there were three possibilities. If the universe had enough mass and energy, gravity would eventually overcome the expansion and pull everything back together in a big crunch, the reverse of the Big Bang. If there wasn't enough mass, the universe would expand forever, gradually cooling and fading in a big freeze. Or if the mass was exactly balanced, the universe might coast to a halt at infinity, asymptotically approaching zero expansion. These scenarios assumed that the expansion was slowing down due to gravity. Everything in the universe attracts everything else, so naturally, the expansion should be decelerating over time. The question was whether gravity was strong enough to eventually stop and reverse the expansion, or whether it would just slow it down but never completely stop it. Then in 1998, everything changed again. Perlmutter, Schmidt, and Reese made their shocking discovery. The expansion isn't slowing down. It's speeding up. The universe is accelerating away from itself, driven by something we call dark energy. Dark energy is one of the greatest mysteries in science. We don't know what it is. We can't detect it directly. We only know it exists because of its effects on the expansion of space. It makes up about 68% of all the energy in the universe, yet we have almost no idea what it is. The simplest explanation is that dark energy is the cosmological constant, the same fudge factor Einstein added to his equations and later regretted. The cosmological constant represents a constant energy density of empty space itself. Every cubic meter of space has a tiny amount of energy inherent to it, and as space expands and creates more cubic meters, more of this energy comes into existence. Think about that. As the universe expands, the total amount of dark energy increases because there's more space and each bit of space carries energy. This extra energy drives more expansion, which creates more space, which adds more dark energy, which drives even more expansion. It's a runaway process, a cosmic feedback loop. This is why the expansion is accelerating. Dark energy is winning the battle against gravity. And unlike gravity, which gets weaker as things spread out, dark energy has constant density. As the universe expands and matter becomes more dilute, gravity gets weaker, but dark energy stays the same. Eventually, dark energy completely dominates, and the acceleration becomes exponential. This leads to what cosmologists call the Big Rip, or more poetically, the heat death of the universe. Here's how it plays out. Over the next tens of billions of years, the accelerating expansion carries away more and more galaxies beyond the cosmic event horizon. The night sky gradually becomes darker as distant galaxies fade from view. After about 100 billion years, only our local gravitational neighborhood remains visible. But the acceleration doesn't stop. Eventually, even galaxies that are gravitationally bound start to feel the effects. As dark energy continues to dominate, the expansion becomes so violent that it starts to overcome even gravity. Galaxy clusters get torn apart, then galaxies themselves, then solar systems. About 50 million years before the end, the Milky Way gets shredded. Stars are ripped from their orbits and sent flying into the expanding void. A few months before the end, solar systems are destroyed. Planets are torn from their stars. Then, in the final minutes, stars and planets themselves are ripped apart. Atoms are torn apart. Even atomic nuclei shredded as the expansion of space overwhelms the strong nuclear force holding them together. In the final fraction of a second, space-time itself is torn apart. The fabric of reality is shredded into nothingness. This is the Big Rip, the ultimate consequence of runaway expansion. This sounds terrifying, and it is. But here's the thing. The Big Rip only happens if dark energy becomes stronger over time. If it's not just a cosmological constant, but something called phantom energy that increases in density, as space expands. Current evidence suggests that dark energy is consistent with being a cosmological constant, which means it maintains constant density. If dark energy is a cosmological constant, the universe faces a different fate: heat death. This is slower and less violent, but equally inevitable. The expansion continues accelerating. Galaxies fade from view. Stars burn out. After trillions of years, all the stars die. The universe goes dark, except for occasional flickers from the last red dwarfs and white dwarfs slowly cooling. Eventually, even these die. The universe becomes a cold, dark expanse of dead stellar remnants, black holes, and slowly decaying particles. The black holes themselves eventually evaporate due to Hawking radiation, a quantum process where black holes slowly leak energy and mass until they disappear in a final burst of radiation. After 10,100 years, even the black holes are gone. The universe has reached maximum entropy. Nothing happens anymore. There's no energy gradient left to drive any process. The universe is in thermodynamic equilibrium, a state of perfect, unchanging uniformity. Time becomes meaningless because nothing changes anymore. This is heat death, not a dramatic ending, but a slow fade into eternal darkness and stillness. The universe doesn't end with a bang or a rip. It ends with a whimper, an infinite, eternal, unchanging void where nothing happens and nothing will ever happen again. But wait, there's one more possibility, and it's somehow even weirder. What if dark energy isn't constant? What if it changes over time in ways we don't understand yet? Then the fate of the universe becomes unpredictable. Dark energy could decay away, leaving the universe to coast into a slow freeze. It could reverse, causing space to contract in a big crunch. It could undergo phase transitions, causing reality itself to fundamentally change in ways we can't predict. Some theoretical physicists speculate about something called vacuum decay. The idea is that the quantum vacuum we live in might not be the lowest energy state possible. We might be in a metastable false vacuum, like a ball balanced on a small dip on a hillside. The ball is stable there, but it's not at the bottom of the hill. If something disturbs it, it could roll down to a lower energy state. If the vacuum undergoes such a transition, a bubble of true vacuum would form somewhere in the universe and expand at light speed, converting everything it touches to this new vacuum state. The laws of physics themselves might be different in the true vacuum. Atoms might not be able to hold together. Particles might have different masses. Reality as we know it would cease to exist. This bubble of true vacuum could be forming somewhere in the universe right now, expanding toward us at light speed. We would have no warning. We couldn't see it coming because it travels at light speed, the same speed as light that would warn us. One moment we exist, the next moment we're converted to a state where the physics might not even allow consciousness or complexity. But here's the thing. This is all speculation. We don't know if the vacuum is metastable. We don't know if such a transition is even possible. And even if it is, the probability might be so low that it won't happen in any reasonable timescale. What we do know is that the universe is expanding. The expansion is accelerating. And this acceleration will eventually carry away all the galaxies, all the evidence of cosmic history, all the structure and complexity that makes our existence possible. Now, I know all of this sounds depressing. The universe is running away from itself. Everything will eventually die or be torn apart or fade into darkness. We're living in a brief window of observability in a cosmos that's ultimately doomed to cold, dark emptiness or violent destruction. But here's another way to look at it. The fact that the universe has a finite age, that it had a beginning and will have an end, is what makes it interesting. An eternal, unchanging universe would be static and boring. But a universe with a history, with a narrative arc from beginning to end, is a story worth experiencing. And we get to experience it. We exist at a time when stars are shining, Galaxies are forming, planets are hosting life. We exist during the stelliferous era, the age of stars, a cosmically brief period when the universe is at its most interesting and complex. Before stars formed, the universe was just hydrogen and helium slowly cooling. After stars die out, the universe will be dark and empty. But right now, right here, in this brief cosmic moment, the universe is alive with light and energy and complexity, and we're here to see it. You are made of star stuff, as Carl Sagan famously said. The atoms in your body were forged in the cores of stars that died billions of years ago. You are the universe experiencing itself. You are a way for the cosmos to know itself. And here's something beautiful. The expansion of space means we're connected to the very beginning. When you look at the cosmic microwave background, you're seeing light that has traveled for 13.8 billion years. That light is older than Earth, older than the Sun, older than the Milky Way. It's light from the Big Bang itself. When you look at that light, you're not just seeing the past, you're seeing your origin. You're seeing the moment when space began expanding, when the universe was born. That light has been traveling through expanding space all this time, and now it's entering your eye, interacting with the rods and cones in your retina, creating signals that travel to your brain, allowing you to perceive and understand your own cosmic beginning. You are an observer at the end of a 13.8 billion year chain of causality, stretching back to the origin of spacetime itself. The expansion of space hasn't disconnected you from your origins. It's carried you forward through time while preserving the light from those origins so you can still see them. That's profound. That's beautiful. That's worth contemplating. Now let's get into something that's going to really twist your understanding of reality. We've talked about how space expands and what that means for the fate of the universe. But there's a deeper question we haven't fully addressed. What does it mean for something to be real if it's beyond the cosmic horizon? This is where the expansion of space intersects with philosophy and the nature of reality itself. And the questions it raises are profound. Right now, there are galaxies beyond the cosmic event horizon that we can never see, never interact with, never influence. From our perspective, these galaxies might as well not exist. No information from them will ever reach us. No signal we send will ever reach them. They're causally disconnected from us. So here's the question. Are those galaxies real? You might instinctively say yes, of course they're real. Just because we can't see them doesn't mean they don't exist. But think about what real means. In physics, we usually say something is real if it has observable effects. If something has absolutely no effect on anything we can ever observe or measure, in what sense does it exist? This is similar to the question of what exists beyond the observable universe. If the universe is infinite, there are regions of space so far away that their light hasn't had time to reach us yet, and due to accelerating expansion, never will. Those regions are beyond our particle horizon. Do they exist? Most physicists would say yes, they exist, even though we can't see them. The laws of physics don't suddenly stop at the edge of the observable universe. Space continues, matter continues. The universe is almost certainly much, much larger than what we can see, possibly infinite. But here's where it gets philosophically tricky. If something is beyond the cosmic horizon, it's not just unobservable now. It's unobservable in principle, not just to us, but to anything in our cosmic neighborhood. It's outside our causal patch of the universe. The concept of a causal patch is crucial here. Your causal patch is the region of space-time that can influence you and that you can influence. It's bounded by the cosmic horizon in space and by the age of the universe in time. Everything within your causal patch is, in principle, part of your universe. Everything outside it might as well be in a separate universe entirely. This leads to a strange implication. If the universe is infinite and the expansion is accelerating, then every observer has their own causal patch, their own observable universe. These patches overlap, but they're not identical. Someone in a galaxy, a billion light years away, has a causal patch that includes regions of space you can never access and excludes regions you can access. In a very real sense, we all live in slightly different universes, defined by our causal patch. Your universe and my universe overlap almost completely because we're on the same planet, but they're technically not identical. And the further apart observers are, the less their observable universes overlap. Now take this to the extreme. In an infinite universe with accelerating expansion, there are observers so far away that our causal patches don't overlap at all. We share no common observable universe. We exist in completely separate regions of spacetime with no causal connection whatsoever. Are we in the same universe? Physically, yes, we're both part of the same spacetime continuum. But observationally, we might as well be in completely separate universes. We can never know about each other. We can never influence each other. There's no experiment that could ever detect the other's existence. This is mind-bending. The expansion of space doesn't just separate galaxies. It fundamentally divides reality into causally disconnected regions. The universe has a kind of built-in privacy where different regions can never know about or influence each other. But here's where it gets even weirder. Some cosmologists take this idea further. If space is infinite and has infinite regions beyond our observable universe, and if the laws of physics are the same everywhere, then somewhere out there, just by random chance, there might be exact copies of Earth, exact copies of you. This is the cosmic inflation argument. During the inflationary period right after the Big Bang, space expanded so rapidly that it created far more universe than we can observe. If inflation is true, the actual universe might be vastly, incomprehensibly larger than the observable universe. In an infinite universe, or even in a finite but sufficiently large universe, every possible quantum state that can exist will exist somewhere, not just once, but infinitely many times. There are only so many ways to arrange atoms in a space the size of the observable universe. That number is huge, but it's finite. If space is infinite, those configurations must repeat. This means that somewhere, far beyond our cosmic horizon, there's another Earth, another you, living a life almost identical to yours, or maybe slightly different due to different quantum outcomes. In fact, there are infinitely many copies of you out there, living every possible variation of your life. This is both philosophically fascinating and completely untestable. Those other versions of you are beyond the cosmic horizon. You can never meet them. You can never know about them. They're in a region of space-time that has no causal connection to yours. Does this make them less real? Or does it reveal that you are not as unique as you thought? That your existence is not a single, unique event, but one of infinitely many similar events scattered across an incomprehensibly vast cosmos? Now, some philosophers and physicists argue that things beyond the cosmic horizon are not physically real in a meaningful sense. They point out that in quantum mechanics, we've learned to be careful about ascribing reality to things we can't measure. The Copenhagen interpretation of quantum mechanics says that quantum systems don't have definite states until they're measured. Before measurement, they exist in superposition, in multiple states simultaneously. If we take this seriously, maybe things beyond the cosmic horizon don't have definite existence until they enter our causal patch and can be observed. Maybe the universe only exists insofar as it can be observed, and regions beyond the horizon are in some kind of undefined quantum state. This is speculative and controversial, but it highlights how the expansion of space forces us to confront deep questions about the nature of reality, existence, and observation. Let me give you another mind-bending scenario. Because of the accelerating expansion, light emitted from galaxies beyond the cosmic horizon will never reach us. But what about light that was emitted before those galaxies crossed the horizon? That light is still traveling toward us, fighting against the expansion. This means we can see galaxies that are currently beyond our cosmic horizon. We're seeing their past, from a time when they were still inside our causal patch. But those galaxies have now crossed the horizon. They're now in a region of spacetime causally disconnected from us. So when we look at those galaxies, are we seeing something real? We're seeing light from their past, but their present is causally inaccessible to us. In a sense, the galaxies we're seeing don't exist anymore, at least not in a form we can ever interact with or observe again. Time and causality become strange when space is expanding. The past, present, and future of distant objects become tangled and confused. We can see objects whose present we can never access. We can observe pasts that are disconnected from any future we can experience. The expansion of space doesn't just separate things in space. It fragments time itself, creating regions of space-time that have no temporal connection to our present moment. Now let me bring this back to something concrete. All of this philosophical speculation about reality and existence isn't just abstract musing. It has practical implications for how we understand the universe and our place in it. If most of the universe is causally disconnected from us, then cosmology, the study of the universe as a whole, is fundamentally limited. We can only study our causal patch. We can only make inferences about the parts of the universe we can observe. Anything beyond that is speculation, no matter how well founded. This means there are questions we might never be able to answer. Is the universe infinite? We don't know, and we might never know, because we can only observe a finite patch. What's the global geometry of the universe? We can measure it locally, but we can't measure the universe as a whole. Are the laws of physics truly universal? Or do they vary in regions beyond our observation? We can't know. The expansion of space imposes fundamental limits on knowledge itself. There are facts about reality that are, in principle, unknowable to us. Not because we lack the technology, not because we're not smart enough, but because the structure of space-time itself prevents the information from reaching us. This is humbling. We like to think that science can eventually answer any question, that given enough time and resources, we can uncover any truth. But the expansion of space tells us that's not true. There are truths forever beyond our reach, hidden behind a cosmic horizon we can never cross. Yet at the same time, it's empowering. The fact that we've figured this out, that we've understood the limits of our own knowledge, is itself a remarkable achievement. We've used observations of distant galaxies, theoretical physics, and careful reasoning to map out not just what we know, but what we can know. We've drawn the boundary of the knowable. And within that boundary, there's still so much to discover. We don't fully understand dark energy. We don't have a theory of quantum gravity. We don't know if inflation really happened, or what caused it. We don't know if there are other forces or particles we haven't detected yet. We don't know the ultimate fate of the universe with certainty. The expansion of space creates mysteries, but it also creates opportunities. Every mystery is a chance to learn something new, to push the boundaries of understanding, to glimpse deeper truths about reality. Before we continue, I need you to do something. Pause for a moment and think about what we've discussed so far. We've covered the speed of light, the expansion of space, cosmic horizons, the fate of the universe, and the nature of reality itself. Does your brain hurt yet? Good. That means you're really thinking about it. Drop a comment and tell me which concept has blown your mind the most so far. And make sure you're subscribed, because we're about to go even deeper into practical implications and mind-bending scenarios. Let's get practical. Let's talk about what the expansion of space means for space travel, for our future as a species, and for our relationship with the cosmos. If you've ever watched science fiction, you've seen spaceships traveling between galaxies, exploring distant corners of the universe, meeting alien civilizations from far away. Star Trek, Star Wars, Battlestar Galactica, they all depict a universe where interstellar, and intergalactic travel is possible. But the expansion of space makes this much harder than science fiction suggests. In fact, it makes much of the universe permanently inaccessible, no matter how advanced we become. Let's start with the basics. The Milky Way galaxy is about 100,000 light years across. That means light takes 100,000 years to cross from one side to the other. At our current technology, traveling to another star in our own galaxy would take tens of thousands of years. The nearest large galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. Even traveling at light speed, which is physically impossible for anything with mass, it would take 2.5 million years to get there. And that's the nearest large galaxy. Most galaxies are much farther away, hundreds of millions or billions of light-years distant. At light speed, you couldn't reach them in the current age of the universe. But here's where the expansion of space makes things even harder. Those distances are the distances now. But space is expanding. By the time you arrive at a distant galaxy, it will be much farther away than it was when you started. Let me give you a specific example. Imagine we develop a spaceship that can travel at 99% the speed of light. That's the theoretical maximum speed for anything with mass, just below the cosmic speed limit. We point this ship at a galaxy 100 million light-years away and launch it. You might think the ship would arrive in a bit over 100 million years, accounting for relativistic time dilation. But you'd be wrong. Because space is expanding, the galaxy is moving away from us as we travel toward it. At 100 million light-years, space is expanding at about 7,000 kilometers per second due to the Hubble expansion. That's 2.3% the speed of light. So as we travel toward the galaxy at 99% light speed, the galaxy is receding from us at 2.3% light speed due to expansion. Our effective closing speed is only 96.7% light speed. This doesn't sound too bad, but remember, the expansion accelerates with distance. As we travel, the galaxy gets farther away, and the expansion rate between us increases. We have to travel faster and faster through space just to maintain the same closing speed. And this is assuming the expansion rate is constant, which it's not. The expansion is accelerating due to dark energy. The farther we travel, the stronger the effect of dark energy becomes, and the harder it is to make progress. There's a distance beyond which, even traveling at light speed, we could never reach a galaxy because the expansion of space between us and the galaxy is greater than light speed. This is the cosmic event horizon I mentioned earlier, currently at about 16 billion light-years. Any galaxy beyond that horizon is forever beyond our reach, no matter how fast we travel. We can see some of them because the light they emitted in the past has reached us, but we can never travel to them. They're in a region of space-time that is causally disconnected from our future. This is a hard limit imposed by the structure of the universe itself. It's not a matter of technology or energy. Even if we could somehow exceed the speed of light, which would require breaking the laws of physics as we understand them, we still couldn't reach galaxies beyond the horizon, because space is expanding faster than any speed. So the universe we can explore is fundamentally limited. We're confined to a region of space within the cosmic event horizon. And due to the accelerating expansion, that region is shrinking in terms of what we can access if we leave now. But even within that region, interstellar and intergalactic travel is incredibly difficult. The distances are so vast, the timescales so long, that even if we could travel at substantial fractions of light speed, exploring the cosmos would take millions or billions of years. This is where special relativity offers a strange loophole. Remember, time dilation means that as you approach light speed, time slows down for you relative to the outside universe. From your perspective on a near-light speed spaceship, a journey that takes millions of years in the rest frame of the universe might only take decades, or even years of your experienced time. This is called the twin paradox, though it's not really a paradox once you understand relativity. If you have identical twins, and one stays on Earth while the other travels to a distant star at near light speed and returns, the traveling twin will have aged much less than the Earth-bound twin. At 99.999% the speed of light, time dilation is so extreme that you could, in principle, travel across the entire observable universe in a single human lifetime as experienced by you. But when you returned, billions of years would have passed on Earth. Everyone you knew would be dead. The sun might have died. The Earth might not even exist anymore. This is one solution to the problem of interstellar travel. Go really, really fast and let time dilation compress the journey. But it comes at a cost. You're not just traveling through space. You're traveling through time. You're effectively one-way time traveling into the future. And this doesn't solve the problem of the cosmic event horizon. Even with time dilation, you can't reach galaxies beyond the horizon because space is expanding between you and them faster than you can travel. So what does this mean for the future of humanity and any other civilizations that might exist in the universe? It means we're fundamentally limited in how much of the universe we can explore and colonize. We're confined to a cosmic neighborhood that, while large by human standards, is tiny compared to the full universe. Most of the cosmos will forever remain beyond our reach. It also means that if there are other intelligent civilizations out there, and they're in distant galaxies, we might never meet them. Not because we lack the technology, not because space is too dangerous, but because the expansion of space itself prevents it. The universe is too large, expanding too fast, for different civilizations to bridge the gaps between them. This is sometimes called the cosmic loneliness hypothesis. Even in a universe teeming with intelligent life, each civilization might be isolated in its own cosmic bubble, unable to communicate with or travel to other civilizations before the expansion carries them beyond the cosmic horizon. Think about this carefully. Right now, there might be thousands or millions of intelligent civilizations in the universe. They might be looking up at their skies, wondering if they're alone. They might be developing radio telescopes, searching for signals. They might be dreaming of interstellar travel and meeting other minds. But if they're far enough away, we'll never know about them, and they'll never know about us. Not because we're not trying hard enough, not because we're using the wrong technology, but because the structure of space-time itself prevents any information from traveling between us. The universe is full of intelligence, full of consciousness, full of minds asking questions about their place in the cosmos. But each mind is trapped in its own causal patch, forever alone in an expanding void. This is both sad and strangely beautiful. Sad because it means we might never have the cosmic community that science fiction promises us. We might be fundamentally alone, not because intelligence is rare, but because the universe is too big and expanding too fast. But it's beautiful because it means that every civilization, every intelligent species, is on its own unique journey. We're not competing with other species for resources or territory across the galaxy. We're not under threat from hostile aliens who want to conquer us. We're simply on our own path, exploring our corner of the universe, developing our own understanding of reality. And here's something profound. If we're isolated by the expansion of space, then the development of intelligence and consciousness is not a single experiment, but countless parallel experiments. Every civilization discovers physics independently. Every civilization develops its own philosophy, its own art, its own culture. Every civilization is a unique solution to the problem of how matter organizes itself into patterns, capable of understanding the universe. The expansion of space means that consciousness and intelligence emerge not just once, but potentially countless times across the cosmos, each instance unique and isolated, each developing its own perspective on reality. You are not just a human. You're not just a member of one species among many on Earth. You're a representative of one experiment in consciousness in a universe that might be running millions are billions of similar experiments, all isolated from each other, all exploring reality from their own unique perspective. Let me take you even deeper now. We've talked about the expansion of space from a cosmic perspective, from a human perspective. Now I want to talk about it from a quantum perspective, because at the smallest scales, the expansion of space reveals some of the strangest features of reality itself. Remember, space isn't really empty. Even in the vacuum of space, far from any matter or energy, quantum mechanics tells us that the vacuum is seething with activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum and paying it back so quickly that they can't be directly detected. This quantum foam, as it's called, is a consequence of Heisenberg's uncertainty principle. The uncertainty principle says that you can't simultaneously know both the energy of a system and the exact time at which it has that energy. There's an inherent fuzziness, an irreducible uncertainty. This uncertainty allows for temporary violations of energy conservation at quantum scales. Particles can borrow energy from nowhere, as long as they pay it back quickly enough. The more energy they borrow, the faster they have to pay it back. But for brief moments, they can exist, popping into existence from the quantum vacuum. Now, here's where it gets interesting. When space expands, it stretches these quantum fluctuations. Imagine a wave pattern drawn on a balloon. As you inflate the balloon, the wave pattern stretches. The wavelength increases. In the early universe, during the inflationary period right after the Big Bang, space expanded so rapidly that quantum fluctuations were stretched to cosmic scales. Tiny, microscopic ripples in the quantum vacuum were inflated to become density variations spanning vast regions of space. These stretched quantum fluctuations eventually became the seeds for galaxy formation. Regions that were slightly more dense attracted more matter through gravity, growing into the galaxies, galaxy clusters, and cosmic structures we see today. Think about that. The largest structures in the universe, superclusters of galaxies spanning hundreds of millions of light years, originated as quantum fluctuations smaller than an atom. The expansion of space transformed the quantum realm into the cosmic realm. This is direct evidence that quantum mechanics operates at all scales, that the weird, probabilistic behavior we see in particle physics experiments is connected to the large-scale structure of the universe itself. The expansion of space creates a bridge between the quantum and the cosmic. But it gets weirder. When quantum fluctuations are stretched by expansion, something strange happens. In normal quantum mechanics, when you measure a quantum system, its wave function collapses. It goes from being in multiple superposed states to being in a single definite state. But during cosmic inflation, quantum fluctuations were stretched so quickly that they couldn't interact with anything, couldn't be measured by anything. They were frozen in their quantum state, suspended in a kind of quantum limbo. Then, as inflation ended and the expansion slowed down, these fluctuations became classical. They transitioned from quantum superpositions to definite density variations without ever being measured. The expansion of space itself caused the quantum to classical transition. This suggests something profound. The expansion of space might be a fundamental mechanism by which quantum probabilities become classical reality. It's not measurement or observation that collapses the wave function. It's the expansion of spacetime itself. This idea is still being explored and debated, but it represents a potential solution to the measurement problem in quantum mechanics. The measurement problem is the question of how and when quantum superpositions become definite classical states. Most interpretations of quantum mechanics struggle with this question. But if the expansion of space can cause quantum to classical transitions, then maybe the growth of the universe itself is what makes reality definite, what transforms quantum possibilities into classical actuality. You exist because quantum fluctuations were stretched by cosmic inflation and became the seeds of galaxies. Your body is made of matter that clumped together because of those quantum fluctuations. You are, quite literally, made of frozen quantum uncertainty, stretched cosmic scales by the expansion of space. Now, let me blow your mind even further. There's a concept in quantum mechanics called quantum entanglement. When two particles are entangled, they're correlated in ways that seem to violate locality. Measure one particle, and you instantly know something about the other particle, no matter how far apart they are. Einstein called this spooky action at a distance and didn't like it. But experiments have confirmed that entanglement is real. Particles really can be correlated in non-local ways. Now here's the question. What happens to entangled particles when space expands between them? If two particles are entangled and then carried apart by the expansion of space, does the entanglement persist? The answer is yes, with some subtleties. Entanglement can persist across expanding space. But as the particles get farther apart, and the expansion carries them beyond the cosmic horizon, something interesting happens. Once particles are beyond the cosmic horizon relative to each other, no information can pass between them. They're causally disconnected, but they can still be entangled. They can still have correlations that would be instantly apparent if they could somehow be brought back together and measured. This means that entanglement, quantum correlation, can exist across causally disconnected regions of spacetime. There can be non-local correlations between parts of the universe that can never communicate or interact. This is deeply weird. It suggests that the universe has a kind of holistic property, a connectedness that transcends space-time separation. Even though regions of the universe can be causally disconnected by the expansion of space, they can still be quantum mechanically correlated. Some physicists believe this reveals something fundamental about the nature of space and time. Maybe space-time isn't the most fundamental thing. Maybe space-time emerges from a deeper level of reality, a level where quantum entanglement is primary and space-time separation is secondary. This idea is at the heart of several approaches to quantum gravity, including theories based on the holographic principle. The holographic principle suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram. Space itself might be an illusion, an emergent property of quantum entanglement patterns. If this is true, then the expansion of space isn't really space getting bigger. It's quantum entanglement patterns rearranging themselves in ways that we perceive as growing space. The universe isn't expanding into anything. The underlying quantum information structure is evolving in ways that manifest as spatial expansion. This is highly speculative, but it illustrates how the expansion of space is connected to the deepest questions in physics. What is space? What is time? How does quantum mechanics relate to gravity? How does the microscopic quantum realm give rise to the macroscopic classical world? The expansion of space sits at the intersection of all these questions. Understanding it might be the key to understanding the fundamental nature of reality itself. Now let me bring this back to something more tangible. The fact that quantum fluctuations can be stretched cosmic scales by expansion has practical implications for cosmology. It means we can use observations of the cosmic microwave background, the large-scale structure of the universe, to learn about quantum physics at energy scales we could never reach with particle accelerators. The cosmic microwave background is a snapshot of the universe when it was only 380,000 years old. At that time, the universe was filled with hot plasma that glowed with thermal radiation. As the universe expanded and cooled, that plasma became transparent, and the light it emitted started traveling freely through space. That light has been traveling for 13.8 billion years, stretched by the expansion of space from visible and infrared wavelengths into microwaves. When we observe the cosmic microwave background today, we're seeing light from the early universe, stretched and cooled by expansion. But here's what's remarkable. The cosmic microwave background isn't perfectly uniform. It has tiny temperature variations, about 1 part in 100,000, across the sky. These variations are the imprint of those quantum fluctuations that were stretched during inflation. By studying the pattern of these variations, cosmologists can learn about the physics of inflation, about the quantum fields that drove the expansion, about the conditions in the universe fractions of a second after the Big Bang. We're using cosmological observations to do quantum physics at energy scales trillions of times higher than what we can achieve in laboratories. The expansion of space has turned the entire universe into a laboratory, an experiment that's been running for 13.8 billion years, revealing the behavior of quantum fields at the highest energy scales. And here's something beautiful. The information encoded in the cosmic microwave background is finite and limited. Because the expansion is carrying distant regions beyond our horizon, we have a finite window of time to observe and study this information before it's lost forever. Future generations, trillions of years from now, won't have access to this information. The cosmic microwave background will have redshifted into undetectability. The evidence of the Big Bang, of cosmic inflation, of the early universe will be gone, erased by the expansion of space. We live in a cosmically privileged time, a brief window when the universe is old enough to have developed intelligent observers, but young enough that those observers can still see the evidence of cosmic origins. This makes our observations precious. The data we collect about the cosmic microwave background, about distant galaxies, about the large-scale structure of the universe, is information that will eventually be lost forever. We're witnessing something that future observers, if they exist, will never be able to see. In a very real sense, we're living at a special moment in cosmic history. Not because we're at a special location, not because we're special entities, but because we exist at a time when the universe is still revealing its secrets, still showing us where it came from and where it's going. Now I want to address a question that might have been nagging at you this whole time. If the expansion of space can carry galaxies apart faster than light, why doesn't this violate Einstein's relativity? How can something move faster than light without breaking the laws of physics? The answer reveals something crucial about what Einstein's theory actually says and what it doesn't say. Einstein's special relativity, published in 1905, establishes that nothing can move through space faster than light. The speed of light is the cosmic speed limit for motion through space. This is an absolute, unbreakable law. No object, no particle, no information can be transmitted through space faster than 299,792,458 meters per second. But Einstein's general relativity, published in 1915, expanded this picture. General relativity describes how space and time themselves can curve, warp, and evolve. And crucially, it places no limits on how fast space itself can expand or contract. Think of it this way. The speed limit applies to traffic on the highway, but it doesn't apply to the highway itself. The highway can be built, extended, or even moved without violating any traffic laws. Similarly, the cosmic speed limit applies to things moving through spacetime, but not to spacetime itself. This distinction is absolutely crucial. When we say galaxies are receding faster than light, we don't mean they're moving through space faster than light. We mean the space between us and them is expanding, such that the distance between us is increasing faster than light could travel across that distance. Imagine two ants on a rubber band. Each ant can walk at a maximum speed of 1 centimeter per second relative to the rubber band beneath its feet. That's their speed limit. They cannot walk faster than that. Now, if you start stretching the rubber band, the distance between the ants increases. If you stretch it fast enough, the distance between the ants can increase faster than 1 centimeter per second, even though neither ant is moving faster than 1 centimeter per second relative to the rubber beneath its feet. The ants haven't violated their speed limit. They're still walking at 1 centimeter per second or less. But the rubber band itself is stretching, carrying them apart faster than they can walk. That's exactly what's happening with galaxies and the expansion of space. Galaxies aren't moving through space faster than light. They're being carried apart by the expansion of space itself. And that expansion doesn't violate any speed limit because it's not motion through space. This distinction shows up in the mathematics of general relativity. In relativity, we distinguish between coordinate distance and proper distance. Proper distance is what you'd measure if you could instantaneously freeze the universe and lay out a measuring tape. Coordinate distance is a label we assign based on our coordinate system. When space expands, proper distances increase. But objects aren't moving in the sense of changing their coordinates. They're staying at the same coordinates while the physical distance between those coordinates increases. It's like if you drew dots on a balloon with a coordinate grid. As you inflate the balloon, the dots stay at the same grid coordinates, but the physical distance between them increases. The dots aren't moving through the grid. The grid itself is expanding. This is why expansion doesn't cause time dilation. If galaxies were actually moving through space at faster than light speeds, which is impossible, they would experience infinite time dilation and all sorts of causality-violating paradoxes. But because they're not moving through space, they're just being carried along by expanding space, there's no time dilation, no violation of causality. From the perspective of someone in a distant galaxy receding from us faster than light, they're perfectly at rest. They're not experiencing any weird relativistic effects. They're just sitting there, and from their perspective, we're the ones receding at faster than light speeds. The expansion is symmetric. Everyone sees everyone else moving away. Now, here's a subtle point that often confuses people. If space is expanding everywhere, why do we say galaxies are moving away from us? Why don't we say we're moving away from them? The answer is that both descriptions are equally valid. The expansion doesn't have a center. It's not like galaxies are flying away from one central point. Rather, every point in space is moving away from every other point. The universe is expanding uniformly. Imagine the surface of an inflating balloon. As the balloon inflates, every point on the surface moves away from every other point. But there's no center of expansion on the surface itself. The center of the balloon is in three-dimensional space, not on the two-dimensional surface. From the perspective of any ant living on the surface, every other point appears to be moving away, and the ant could reasonably think of itself as stationary. The same is true for the three-dimensional space we live in. It's expanding uniformly, and every observer can consider themselves at rest with all other points moving away from them. There's no preferred reference frame, no absolute center of expansion. This symmetry is actually evidence for the expansion. If galaxies were just flying through space away from a central explosion, we'd see them all moving in roughly the same direction relative to us, and their speeds wouldn't correlate so neatly with distance. But because the expansion is uniform, every galaxy's recession speed is proportional to its distance, creating the Hubble relation we observe. Now here's something that will really twist your brain. Because the expansion is accelerating, there's something called the Hubble constant, which actually isn't constant at all. It changes over time. The Hubble constant measures the current rate of expansion, about 70 kilometers per second per megaparsec. But in the past, when the universe was smaller and denser, the Hubble constant was much larger. The expansion rate was faster. And in the future, as dark energy continues to dominate, the Hubble constant will actually decrease, even though the expansion is accelerating. This seems paradoxical. How can the expansion be accelerating while the Hubble constant decreases? The answer has to do with what the Hubble constant actually measures. It measures the expansion rate per unit distance. As the universe gets bigger, even though the absolute rate of expansion is accelerating, the expansion rate per unit distance can decrease because there's more distance over which the expansion is occurring. Think of it like a car accelerating. The speedometer might show increasing speed, analogous to accelerating expansion, but the rate of acceleration per mile traveled might decrease as the car gets faster and travels more miles per unit time. This is one of the subtleties of cosmology that makes it so fascinating and challenging. The mathematics of expanding space, of relativistic cosmology, is subtle and non-intuitive. Our everyday experience gives us no preparation for understanding these concepts. But here's what's amazing. Despite the counterintuitive nature of these ideas, we can test them. We can make predictions based on the mathematics of general relativity and the expansion of space. And then we can observe the universe to see if those predictions hold. And they do. Over and over again, observations confirm the predictions of general relativity and cosmic expansion. The theory works. The mathematics describes reality. This is what's so beautiful about physics. We can use abstract mathematics, equations that seem divorced from everyday experience, to make precise predictions about the universe. And when we check those predictions against observations, we find that reality actually follows the math. The expansion of space is one of the most counterintuitive, mind-bending concepts in all of physics. But it's also one of the best confirmed. We've tested it in countless ways, from the cosmic microwave background to distant supernova to the large-scale structure of galaxies. And every test confirms that space really is expanding, that general relativity really does describe how spacetime behaves.